Previously, we've studied parameterized surfaces, and now we're going to move on and talk about surface integrals. So we might have to use that parameterization that we talked about last time. To begin our discussion in this video, though, I want to do a brief little warm-up here. So it says we have a parameterization here for a curve. Fill in the table below. So what's the quantity? What's the formula? Pause the video. Take a shot. Okay, well, arc length, you might remember this as the integral from a to b of the length of the derivative vector. Okay, and then, so then in the second box, we kind of look at that and we're like, oh, well, that's just the scalar line integral. Integral of g along x. Okay, so that should be mostly a review. And now here in this next one, again, pause video, take a shot, and see if you can complete this table. Okay, well, in last class we were talking about surface area via a parameterized surface, and we said, well, the surface area is just going to be the double integral over our domain of the length of the cross product of these tangent vectors, which really is just the normal vector, ds dt. Okay, and then this next one, this is the one where you might not know the answer, and that's okay, but this is sort of the analog to what we saw in the above table. It would be the double integral over d of h of x of s of t, so using a parameterization for the surface, and then the length of the normal vector ts cross tt, and then ds dt. Okay, so that's what we want to talk about today, and that last definition is actually the scalar surface integral. So we have to have a parameterization of a smooth surface. And again, if you need to look up the definition of smooth, I would refer you back to 7.1. Make sure you have a solid understanding of that definition. And then, so we have a parameterization, and then we have a continuous function that is that we're looking at on this certain domain, and so then we say the scalar surface integral looks a lot like what we used to use for a scalar line integral. Now we're just doing it over a surface, and so again we would use a parameterization for the surface. That's what the x of s of t is, and we substitute that into our continuous function, and then we have to multiply by that length, and ts cross tt, we saw that last time as the unit normal vector. Okay, and then just note when g of x and y z, that's that continuous function, if that is just 1, well, what happens? Well, if this whole thing is just 1, then really that's just, well, we could omit that and just say it's ts cross tt, and then, well, we recognize that as just the surface area from last time. Okay, so kind of a neat little connection. So just be aware of that. All right. Next, we just want to do a quick example here. So we have a surface defined according to that parameterization, and then we are given bounds, okay, and we want to evaluate this scalar line integral, okay, where our continuous function is just x. All right, so we need to find a few different things, right? We need to perhaps find ts and tt. Okay, and I should remember my vector signs. Okay, well, ts, if we do that, that should just be 1, 1, and then t. And then similarly, tt should be 1, minus 1, and s. Okay, so then when we cross these, ts cross tt, it is going to yield s plus t, and then negative of s minus t, and then lastly minus 2. Okay, so then the length of TS cross TT is precisely the square root of 2s squared plus 2t squared, and then plus 4. Okay, so again, I did a lot of this off screen, so feel free to do the same. And so then when we look at now I'm ready to do the scalar surface integral. So I do double integral over s squared plus t squared less than or equal to 1. Okay, so then I use a parameterization for x, right? And that is s plus t. And then I do square root of 2s squared plus 2t squared plus 4, okay, ds dt. And then now here, this is where I would say this is kind of ugly. Let's maybe switch to polar. And so when you switch to polar, it does give you 0 to 1, 0 to 2 pi, and then you get r cosine theta plus r sine theta, and then square root of 2r squared plus 4, and then r dr, or d theta dr. Okay, and so you do a bunch of calculations or stick it in Wolfram alpha, and you get out 0. Okay, so just an example of the scalar surface integral, and again, it looks a lot like a scalar line integral. The only difference is that instead of a line, we have a surface. Okay, more to come on this in the next video.